Hello, everybody. I'm Cristiano Ciuti, and I'm pleased to give you this seminar on open quantum many-body systems. First of all, let me thank Professor Jean Dalibard for the kind invitation and for giving me the opportunity to present this research at Collège de France. Here is the outline of this presentation. I will start with a general introduction, outlining the concepts, systems, challenges, and methods in the field. Then after this general introduction, I will present three emerging topics and their related perspectives. In particular, I will talk about recent results on dissipative phase transitions and reservoir engineering, the problem of multimode circuit QD, in particular in the quantum impurity regime, and I will show how a quantum system can become its own buzz due to many-body interaction. And finally, I will talk about the role of dissipation in ion entangling quantum algorithms. In particular, I will talk about the role of dissipation and decoherence in the noisy quantum Fourier transform. During the talk and at the end, I will warmly acknowledge the many collaborators that have been involved in this research. And I will also draw comparison with the class given by Professor Jean Dalibard before this seminar. Let's start with the general introduction. So what is an open quantum system? An open quantum system is a quantum system where its dynamics is significantly affected by the environment. In other words, open means that the environment matters. And in this talk, we'll concentrate on open quantum many-body systems. These complex systems are obtained by considering many individual open quantum systems, like for instance, a lattice of coupled cavities. In these open quantum many-body systems, there is a Hilbert space, which is the product of individual Hilbert space. And so in general, we have a large Hilbert space, which exponentially grows with the number of fundamental units. So this many-body system is open. So in general, the state of the system is described by its reduced density matrix, which in general is a mixed density matrix. And the reduced density matrix is an Hermitian operator. So it can be diagonalized in terms of eigenstates and eigenvalues. And so the eigenstates are pure many-body states, and the eigenvalues are the corresponding probability. The dynamics of an open quantum many-body system is given by a density matrix whose dynamics is given by a master equation. Okay, so the field of open quantum many-body system has a strong link with the emerging field of quantum information, with the real quantum processor. But in a real quantum processor, basically you have a collection of qubits, which forms a many-body system. And usually quantum algorithms, like for example, the quantum Fourier transform, pursue quantum advantage by exploiting many qubit entanglement. And the calculations basically are obtained by starting from an initial state and then letting evolve via a unitary evolution, which is given by the Hamiltonian of the system. And in presence of dissipation and decoherence, the dynamics of the system is non-unitary. And to understand really microscopically what happens in a real quantum computer, you really have to take into account the dissipation and decoherence. And to do that, you have really to deal with open quantum many-body physics. In recent years, this paradigm has been reversed. In fact, while in traditional quantum information, dissipation and decoherence are seen as a problem for quantum computation and are the sources of the quantum errors, in recent years, it has been shown that under adequate conditions, basically decoupling to the environment can be used as a resource. And in particular, for example, by exploiting the coupling to the environment, it is possible to prepare a quantum state in non-trivial quantum phase. And it is possible also to use a reservoir to perform computation. Now, just to give you an example of what happens in real laboratories, yeah, just to give you an example of a non-trivial quantum phase which has been obtained through reservoir engineering. The experiments reported here has been performed at the University of Chicago in the groups of John Simon and David Schuster. And so basically, the system consists of a superconducting quantum circuit, which realizes a system which can be described by a Bose-Hubbard chain. So there is a chain of individual sites where with on-site interaction for the microwave photons and some hopping between different sites. And this system can be driven coherently through microwave fields, and it is coupled to an artificial environment, which is used as a dissipative stabilizer. In other words, photons are injected into the system, and by judiciously tailoring the coupling to the environment, it is possible to prepare the system in a non-trivial phase, which is the Mott insulator. A Mott insulator is a phase basically where there is one photon, exactly one photon per side. Just to give an example of what can be done in experiments. An open problem that is much explored in the literature is the understanding of non-equilibrium phase diagrams. And another question, which is very important in the literature, is it possible to create quantum simulators of a closed system by using open quantum systems? Okay. Now, as I said earlier, the dynamic of the density matrix is governed by a master equation, so a differential equation for the density matrix. So a key role is played by the Liouvillean superoperator, which enters this master equation. Now, if this Liouvillean superoperator is characterized by a spectrum of complex eigenvalues. The eigenvalues are complex because the Liouvillean superoperator is non-Hermitian. Now, the eigenvalue lambda equals 0 corresponds to the steady state solution of the density matrix. In fact, it corresponds to the solution such that the time derivative is equal to 0. The other complex eigenvalues in the complex plane are instead responsible for the transit dynamics away from the steady state regime. Just to give you an example of master equation and to make this Liouvillean superoperator a bit more concrete. So under the quite general conditions of an environment which is weakly coupled to the system and with a very short memory, the master equation for the density matrix of the system can be written in this so-called Lindblad form. So the time derivative of the master equation has a unitary contribution, which depends only on the quantum Hamiltonian, and then has a non-unitary evolution, which depends on the coupling to the environment. In particular, for any environment dissipation channel, there is a dissipation rate, which quantifies the coupling, and then jump operators, which corresponds to the different channels. So this part consists actually of Lindblad dissipators, which are responsible for dissipation and decoherence. It depends on the type of jump operators that you have. Now, if you look at the dynamics in the long time limit, the density matrix of the system tends for very long times to the steady state. And approaching the steady state, the transit dynamics is actually dominated by the eigenvalue of the Liouville operator, such that it has the absolute value of the real part, which is the smallest one. So it's actually the eigenvalue closest to the origin. And if you take lambda as the minimum of the absolute part of the real part, you see that the density matrix tends to the steady state with this asymptotic decay rate. So lambda is called in the literature asymptotic decay rate, and is also called the Liouvillean frequency gap. Now, in the physics of open quantum many-body problem, there are many challenges. In fact, at the same time, you have to deal with non-unitary, non-equilibrium dynamics, which is associated to the open character of the system, and with high entanglement and strong correlations, which is characteristic of strongly correlated quantum many-body system. Let's be clear. For this problem, there is no theory of everything, no unifying theory. However, in recent years, there has been a tremendous progress in many directions. And here in this slide, I try to give you a picture of what is going on, even though this slide is far from being exhaustive. So there have been significant progresses in the development of sophisticated mean field methods, like the Gutzwiller method, where the density matrix of the system is factorized, the cluster mean field theory. Then there's been great progress in variational methods based on faithful representations of the density matrix in terms of matrix product operators for 1D systems, tensor networks, and also artificial neural networks. Then there have been significant advance for methods which are suited for low entropy systems, like the corner space method, which will be described in the talk. And then there are other methods like diagrammatic expansion, like the linked cluster expansion, exact approaches based like the complex P representation, and also stochastic approaches based on trajectories, like those based on the Wigner representation, Gaussian trajectories. And there are also hybrid methods which combine several of these techniques. Now, just to give you a flavor of what is going on, let me just briefly remark the progress that has been done recently on neural networks for open quantum systems. 4 independent works have been published at the same time on this subject, and one work comes from our group, in particular by the PhD thesis of Filippo Vicentini. So let me describe the basic idea behind this method. So the idea is, okay, you have an open quantum system, like for example, a chain of spins with some dissipation. And so the system is described by a density matrix, which in general is a mixed density matrix. So the basic idea here is to enlarge the Hilbert space by introducing ancillary degrees of freedom, okay? And so the idea is to describe the system mixed density matrix as a pure state in the extended Hilbert space. And so the density matrix for the system is retrieved by tracing the pure density matrix of the extended space over the ancillary degrees of freedom. Then once you have considered the extended space and its purified wave function, basically we use a neural network variational answer for such wave function. In other words, this wave function is represented in terms of a neural network function, which depends on the physical parameters, which in this case are spin, and then it depends on the ancillary degrees of freedom and also some hidden degrees of freedom. Okay, to find the optimal solution within a variational method, we have to find a variational principle. And so this can be done by introducing a cost function a cost function which is always larger or equal to 0. And this cost function is essentially linked to the Liouvillean superoperator of the master equation. The function defined here is always positive or equal to 0, and is equal to 0 if and only if the variational wave function is equal to the steady state. So by minimizing this cost function, it is possible to find the optimal variational wave function. And this minimization can be performed by Monte Carlo sampling and stochastic gradient techniques. And so the system tends to, after some iterations, you find the optimal parameters, and you can find a representation of the density matrix. Another class of systems, of methods for open quantum body systems tries to exploit what happens when the system has a low entropy. So let's consider the density metric. As I told you before, the density metric can be expressed in terms of its eigenstates, which form an orthonormal basis, and its eigenvalues, which are probabilities. In the following, we will consider the probabilities to be ordered. It means that P1 is the most probable eigenvalues, P2 is smaller than P1, P3 is smaller than P2. So the probabilities are ordered in a descending order, okay? Now, this is the density matrix. To quantify the mixed character of the density matrix, a very important quantity is called von Neumann entropy, which is defined here. And when you have a system which is in a pure state, basically what you have in a system with a pure state, the entropy is equal to 0, okay? But when the entropy is moderated, basically it is possible to represent the density matrix with a small number m of eigenstates. In particular, it is possible to consider the m most probable eigenstates of the density matrix. And the corner space is exactly defined by, it's the subspace of the Hilbert space, which is spanned by the m most probable eigenstates of the density matrix. So when the entropy of the system is very small, it is possible to faithfully represent such density matrix with a small number of m. Instead, when the system is very entropic, m can tend to the dimension of the Hilbert space. So when the entropy is small, actually only a small portion of the Hilbert space matters. And so some methods can be optimized using this basic fact. And in fact, for example, in the context of spatial renormalization technique, a method has been developed in our group for systems with moderate entropy. And I'm not describing here the method, but this method will be used in the application shown later. Okay, so this is for the general introduction. Okay, so now after having described the general concepts, I will describe the first of the recent topics that are emerging. I will talk about dissipative phase transition and reservoir engineering more in detail, and I will also show you several experiments in different physical platforms in the field. Okay, first of all, let's define what is the dissipative phase transition of mth order. Okay, so as we consider a system, it's a reduced density matrix in the steady state. So rho SS is the steady state density matrix. And this steady state density matrix depends on some parameter and on some thermodynamical parameter. Okay, and now if you want to calculate the expectation value of an observable, you have just to trace the density matrix in the steady state with such operator. Good. Now, once you have this expectation value, we can take its limit when the thermodynamical parameter goes to infinity. The thermodynamical parameter can be, for example, the number of sites in a lattice system. And once we have taken the thermodynamic limit, we look at the empty derivatives. And when the parameter goes to some critical value, if there is a singularity, we say that for the m derivative, we say that the phase transition is of m order. So this is quite rigorous definition of dissipative phase transition. And for more details, I encourage you to look at this very detailed and clear reference by Fabrizio Minganti, who was a PhD in our group. So as I just anticipated, for example, if you have a lattice system, the thermodynamical system is achieved when the number of sites goes to infinity. But in the case of bosonic fields, there's also another thermodynamic limit, is when the number of particles per site goes to infinity. Now, if you want to describe dissipative phase transition, it's quite instructive compared to quantum phase transition for closed systems. Now, in the case of quantum phase transition, the dynamical operator is the Hamiltonian of the system, which is the Hermitian operator. Instead, in the case of dissipative phase transition, the dynamical operator is the Liouville's operator, which is not Hermitian. So that's the first difference. In the case of a quantum phase transition for a closed system, one method is the ground state of the system, which is the eigenstates of the Hamiltonian with the lowest energy. In the case of dissipative phase transition, the analogous of the ground state is the steady state, which corresponds to the zero eigenvalue of the Liouvillean superoperator. Concerning the definition of the singularity, this is similar in both cases in the sense that we detect a singularity in some observables. For quantum phase transitions, the observables are calculated in the ground state. For dissipative phase transition, the observables are calculated in the steady state. And that another important property of a quantum phase transition is when you approach the critical point, there is a closing of the Hamiltonian gap. So it means that at the critical point, there is some emerging degeneracy of the ground state with some other state. In the case of the dissipative phase transition, there is a related phenomenon, which is the closure of the Liouvillean gap. Indeed, it can be proved that when you have a dissipative phase transition at the critical point, in the thermodynamical limit, the Liouvillean gap goes to zero. And in the case of first order dissipative phase transition, actually the thermodynamic limit, the Liouvillean goes to zero just in one point. If you have a second order dissipative phase transition with a discrete symmetry breaking, basically the Liouvillean gap vanishes above the critical point in the region where the discrete symmetry is broken. Okay, just to give you an example of dissipative phase transition. So yeah, I will consider a chain of nonlinear optical cavities where in each cavity there is a Kerr nonlinearity. So a Kerr nonlinearity is basically a photon-photon interaction, which is due to a third order optical nonlinearity. Okay, so when you have two photons in the same cavity, there is an interaction energy, which is responsible for the nonlinearity. Okay, remarkably, in this kind of system, a dissipative phase transition of the first order emerges in the limit of a large number of cavities. So here I'm plotting the result for the steady state population of photons per unit size as a function of the photon driving, which is applied to each cavity. And on the right, you can see results for a two-dimensional squared lattice. And on the left, you can see results for a 1D chain. And as you see, when you increase the lattice size, in the 2D case, there is a clear first order phase transition which emerges. On the other hand, if you consider a 1D chain, you can see that the dissipative phase transition is replaced by a crossover, and there is no singularity emerge. And notice that we are in a regime where in an individual cavity, the system presents an optical stability. So putting together many cavities in such thermodynamic limits, the interaction between the cavity and the nonlinearity produce this first order dissipative phase transition. It's quite interesting to look at the trajectories in the two cases. For example, for the 2D case, here we see an individual trajectory for a single site, the blue line, and the orange line is actually the average of the trajectories on the different sides. And you see that everything is synchronous. You see that the density in each, the number of photons in each cavity fluctuates, but then it jumps between two very distinct phases with different densities. And you see that the jumps are simultaneous and synchronous for all the cavities. That's what happens at the critical point, where there is a coexistence of the two phases. That's the jump between these two phases, which is responsible for the first order dissipative phase transition. Instead, in the case in a 1D case, you can see that there are no two clear phases, and there is no synchronous behavior of the different lines. So this is let's say, an evidence in real time of the critical behavior in 2D and the non-critical behavior in 1D. It's interesting to look at the asymptotic decay rate. So here I'm showing the transient of the population of bosons per site. So it's the difference between the boson photon population at time t and the steady state in absolute value as a function of time. And this is a log scale, so you can see the results for different lattice sizes. If you do it 2D, when you increase the number of sites, you can see that the decay becomes slower, slower, slower. And indeed, you have a critical slowing down with the time which diverges to infinity when the number of lattice sizes goes to infinity. And that's associated to the presence of this dissipative phase transition. By contrast, in the 1D case, you have a slowing down, so increasing the size of the chain, the rate becomes faster, but eventually it saturates to a finite value. And this corresponds to the crossover. If you look at the Liouvillean gap, which is basically the asymptotic decay rate as a function of the gravity, you can see that in 1D, when you increase the lattice size, the Liouvillean gap goes to 0, and there is a closing of the Liouvillean gap. Instead, in 1D, by increasing the length of the chain, the Liouvillean gap eventually saturates to a finite value. And so in 1D, it's another manifestation of the absence of the dissipative phase transition 1D and the presence of the dissipative phase transition in 2D. And this kind of physics has been observed recently in the experimental group led by Alberto Bramati at the Laboratoire Matériaux université, with whom we have a fruitful collaboration since many years. So the idea is to use as nonlinear medium a semiconductor microcavity, which acts as a carrier medium, and then to create a system via a top hat excitation. So basically, by using a top hat excitation, it is possible to define a 2D sample. And the boundary conditions for this system are diffusive. And then basically the idea is to increase the size of this system to achieve a thermodynamical limit. And indeed, by measuring at the population as a function of intensity for different lattice size, it is very nice to observe the emergence of the dissipative phase transition. And this dissipative phase transition occurs with a 2D spot while it disappears if you use a 1D spot. To study the properties of the dynamical properties of critical points in dissipated phase transition, a very powerful technique is based on the so-called dynamical hysteresis. So basically, the idea is to sweep the parameters of the system through some critical point and to measure some dynamical hysteresis loop in some observers. For example, these are experiments by the group of Jacqueline Bloch at Laboratoires C2N, Paris-Saclay. And so basically the idea is that for example, you sweep the driving intensity on a semiconductor microcavity in a very non-adiabatic fashion, and then you measure at the transmission and you see this dynamical hysteresis loop. So the nice thing is that the area defined by the hysteresis loop is very sensitive to the critical physics. So in particular, if the hysteresis area is plotted as a function of the sweep time, basically a power law behavior is exhibited. And so by looking at the decay of the dynamical hysteresis area as a function of this sweeping time, it is possible to extract information about the critical point. So these are experiments, these are theoretical calculations that we perform in collaboration with the Jacqueline Bloch's group. And this physics has some connections with the Keeble-Zurek mechanism for closed quantum systems across critical points. It's really the physics of non-adiabatic changes around the critical points. A very interesting system and physics can be achieved instead of considering a traditional driving of an optical microcavity, one considers two-photon pumping. So two-photon pumping is described by this Hamiltonian. So basically, we consider still a Kerr system where there is some photon-photon interaction quantified by the interaction U. And then there is a two-photon coherent pumping term described by this term, where A dagger is the creation of one photon, and A is the distraction operator of one photon. And then if we consider a situation where there is a dominant two-photon dissipation channel. It means that photons are dissipated in pairs. And in terms of the Lindblad-Master equation, this is represented by this kind of Lindblad dissipator, where the jump operator, instead of being A, is A dot. And so we will consider the situation where the two-photon dissipator, quantified by the dissipation rate eta, is dominant with respect to the one-photon dissipator, which is characterized by the jump operator A and by the dissipation rate gamma. So one can wonder, how is it possible to realize this exotic Hamiltonian? Well, it's actually relatively simple and can be used by, it can be obtained by using ancillary cavity. So the system is a good high quality factor cavity, and the environment, the reservoir, is given by a bed cavity, which is a low quality factor resonator. And then the good cavity, the bed cavity, are coupled by Josephson junction, which produces a nonlinear coupling between the two resonators. And so basically, to create this two-photon Hamiltonian, you have just to send two microwave fields with the right frequencies, and through parametric processes generated by the nonlinear Josephson junction, it is, and tracing out the reservoir degrees of freedom, it is possible to engineer this kind of effective Liouvillean for the system where you have two-photon driving and two-photon dissipation. And if the coupling to the reservoir is very strong, the two-photon dissipation can be done. This kind of reservoir engineering has been pioneered by the group of Michel Devoré, and the first author is Zaki Lektak, who is now researcher in Paris. So what happens when we consider this regime where the two photon loss rate is dominant with respect to the single photon loss rate? Well, if this is the case, since the photons are injected in pairs and they are lost in pairs, there is a symmetry in the system, which is the parity of the photon number, which is conserved. And so for this kind of open quantum system, the parity of the photon number plays an important role. And an important role is played by the so-called photonic cut state, which are defined here. So there are two cut states, plus and minus, which depends on the complex number alpha. So one state, the state plus, is obtained by summing the coherent state with amplitude alpha with the coherent state with opposite phase. And the minus photonic cut state is obtained just by subtracting the state. And these photonic cut states play a fundamental role in the dynamics of this system for two reasons. First of all, the eigenstate of the symmetry of the system, which is the parity operator. So the C plus state is a state which is an eigenstate of the parity with eigenvalue +1, so it's an even state. And the minus state is an eigenstate of the parity operators with eigenvalues -1, so it's an odd state. And the second reason is that such cut states are eigenstates of the jump operator associated to the two photon process. And this is in contrast with the coherent state, which alpha, which are not eigenstates of the parity operator, and they are eigenstates of the one photon jump operator. And indeed, it can be proved that in presence of a strong two photon driving, strong two photon dissipation rate, the dynamics of the system in question is confined to a two-dimensional manifold, which is spanned by the even and odd cut state. So the cavity system, which initially has a Hilbert space with an infinite number of Fock number states, actually the effective dynamics of the system is confined to a two-dimensional Hilbert space. So the system actually behaves like a qubit, and an effective spin 1/2. And that's the idea of the photonic cut qubits, which has been developed at Yale. And this is the experimental demonstration, for example, of the appearance of photonic Schrödinger cut states in the transit dynamics. Okay, so if each cavity where there is two photon pumping and two photon dissipation, if each cavity behaves like a spin, a two-level system, now if you couple many of these cavities, you can wonder, can a chain of these cavities with two photon driving dissipation can behave as a quantum magnetic system, and in particular as a quantum magnetic oscillator, simulator? And the answer is yes. And we have explored this in collaboration with Vincenzo Savona at the École Polytechnique Fédérale in Lausanne, Switzerland. So I show here results which have been achieved via the corner space renormalization method, which was developed in our group. So basically, here I just plot the results of the four-normal entropy, which was defined before, and of the parity of the total photon number operator in the chain. So basically here you see on the left the entropy and on the right the parity. Both quantities are plotted as a function of G, which is the two photon driving amplitude normalized to the dissipation rate. And here for simplicity, we are considering dissipation rate for the single photon channel equal to the two photon dissipation rate. And the results are plotted for different lattice size. So in the case of entropy, when the driving is equal to 0, the system is in its vacuum state. So the entropy is 0 because the system is a pure state, the vacuum state. And the vacuum state has 0 photons, so the parity is 1. So when the driving is 0, you have 0 entropy and parity is equal to 1. But when we increase the driving, what happens, since the system is open, there is some entropy, which increases. But you see that when you increase the number of lattice size in this two-dimensional lattice configuration, you can see that actually there is a maximum for the fundamental entropy, which is appearing at intermediate drive. And then for large driving, the entropy goes down eventually. And concerning the parity, you can see when you drive, the parity is decreases because of the single photon dissipation channels. When you lose one photon, you change the parity. So on average, the average parity is decreased. But this decrease actually it becomes faster and faster when the size of the lattice is decreased. Okay, now it's interesting just to point out that to model 8 by 8 sites, in principle, it's a very challenging task because the dimension of the Hilbert space, if you consider, for example, a cutoff of 4 photons per site, the dimension of the Hilbert space is of the order of 10 to the 44. By using the corner space randomization and the fact that the system has a moderate entropy, we were able to converge with only 2,500 states. And this is a considerable simplification, which allowed us to solve to this lattice sizes. Now, as it's done often in the physics of finite size scaling of dissipative phase transition, when you have a result for one observable for different lattice size, it is interesting to consider renormalized quantum. In particular, the parity is multiplied by the lattice length to the power beta over nu, while the driving is subtracted by constant value and multiplied by the length to the power 1 over nu. Now, if you choose the exponent beta and nu in a judicious way, it is possible to let these curves collapse into single curve. And you see really the emergence of a critical point at some intermediate value. So the bottom line is that there is a dissipative phase transition which emerges as proved by this universal scaling behavior. The remarkable thing is that to get this universal collapse, you have to use the 2D quantumizing critical exponents. This seems at first quite crazy because I'm starting from a bosonic system where there is 2 photon driving, 2 photon photon interaction, and 2 photon dissipation. And then you see an observable which shows the critical exponents of the quantum model in a driven dissipative system. And this can be understood if you do a projective mapping. So in the case of one cavity, we see that the system can describe by a spin. You can call spin up the Schrödinger, photonic Schrödinger cut state with parity even, and spin down the odd photonic cut. And if you, this is for the local state, if you do a projective mapping, the Hamiltonian of the system in terms of the bosonic operator can be mapped into this spin Hamiltonian, which actually is the Hamiltonian of the quantum transverse XY model, and which has a critical point which belongs to the universality class of the 2D quantum Hansen model. And what about the 2 photon dissipation channel? Quite remarkably, if you transform these jump operators for the 2 photon process in terms of the spin operator, you can see that it's a multiple of the density. So basically, thanks to this reservoir engineering, the system can be projected into a spin, which has a critical point like in the quantum Hansen model. And the 2 photon dissipations actually produce no jump. So the only jump is due to single photon losses, which creates spin flip processes. But when the 2 photon processes are dominant, the single photon losses is just a perturbation, and it plays a similar role to temperature in quantum phase transition for closed systems. So it is possible to realize a quantum simulator of a closed quantum magnetic system using a driven dissipated one, which is a pretty remarkable result. And this game can be extended even further. For example, by using in a judicial way ancillary cavities, it is possible to engineer non-local dissipation. So basically, it is possible to create effective jump operators for the system, which are non-local into the bosonic operators. And in particular, it is possible to create antiferromagnetic interaction in a purely dissipated way, as shown in this work of our group by Tejalin and Ariane Sore. And so this is quite exciting because this opens the way to the study of frustrated quantum magnetism using photonic system and the reservoir engineering. Okay, I hope I give you some general flavor of the exciting research in this direction. Now, I consider another open quantum many-body system, but in the context of multimode circuit 3D. So this is a work, recent work, which has been done in collaboration with an experimental group led by Vladimir Manucharyan at the Joy Quantum Institute at the University of Maryland. So basically, it's the quantum purity regime of multimode circuit quantum electrodynamics. And in particular, I'll show you how this kind of system can realize a quantum system which can become as its own bus. We'll see what it means later more in detail. Okay, so how this physics is realized. So what we wanted to explore is the physics of a multimode bosonic system with a spectrum of eigenvalues of a frequency which depends on the mode. And this multimode bosonic system is our target system, which is coupled to a single two-level system, which acts as a quantum impurity. So here, the environment is the quantum impurity, which is coupled to the multimode bosonic system. So we want to study the many-body physics, which is created by a single two-level system. And in practice, in the lab, this kind of model can be realized using a transmission line resonator, superconducting transmission line resonator, which hosts many microwave modes, actually starting from radio frequency to microwave frequencies. And the two-level system is achieved via a fluxonium atom, which is an atom with a strong anharmonicity, so a good two-level system, and with high degree of coherence, so very sharp alignment. And this is the schematic of the system. Basically, we have the transmission line, which is coupled galvanically to this artificial atom. And the coupling is achieved via this Chaire inductance. And the X in the following is a fraction between 0 and 1. It defines the fraction of the fluxonium inductance, which is shared by the artificial atom and by the transmission line. And X can be varied between 0 and 1 in a purely geometric way. So how is the transmission line achieved? The transmission line is actually consists of 20,000 large Josephson junctions. And this is why one has to use this Josephson junction array. The reason is that it's very practical to have a high impedance. And with the high impedance, it is possible to have a compact transmission line. And the fluxonium atom is basically a small Josephson junction, which is surrounded by an inductive loop. And as you see, this is the shared inductance fraction, which is responsible for the coupling between the fluxonium and the multimode cavity. Okay, this system can be studied through by microwave spectroscopy. So this is the spectrum of the bare transmission line. So just the transmission line. You see there are many resonances which correspond to the mode starting from roughly 50 megahertz going to 10 gigahertz. And so here you see the mode frequency as a function of the mode number. You can see there is a large region where the dispersion is approximately linear. Due to the high impedance of the line, the light speed in this transmission line is very slow. It's about 140 times smaller than the speed light in batch. Okay, so this system, even if it's just a two-level system, is still a quantum many-body system because we have many modes, and so the size of the Hilbert space is very large. So I will describe now the quantum Hamiltonian of this system. Like in electromagnetism, in the context of circuit quantization, there are different choices of variables which are possible. This choice of variables, which is depicted here, corresponds to the so-called flux gauge. So basically, the transmission line is represented through this Foster decomposition in terms of inductances and capacitances. And then the variables of the artificial element are just the flux and just from charge operator variable. So by using the standard circuit quantization procedure, it is possible to obtain exactly the Hamiltonian of the system, which can separate it in three terms. One is the atom Hamiltonian, one is the Hamiltonian of the modes of the transmission line, and one is the coupling. In the flux gauge, there is a coupling between the flux operator of the Josephson junction and the bosonic operators of the transmission line. Now, this flux gauge has two inconvenient features. First of all, the atom mode coupling diverges at high frequency. And this is a problem because if you want, when you want to do calculation, you have to truncate at some cutoff energies. And so due to this divergence, this is very impractical. And the other inconvenient feature of the flux gauge is that, okay, you can separate the atom Hamiltonian from the mode Hamiltonian and from the interaction, but this is possible only if the atom parameters are renormalized. In particular, the inductive energy of the artificial atom in this gauge is renormalized by the transmission line. And this is not convenient because you want that the atom be fixed. So that's why we explored a different gauge, which is the charge gauge, and which is described here. And so basically, it's another choice of parameters. I will not enter the details. And also in this gauge, you can separate an atom Hamiltonian, a mode Hamiltonian for the transmission lines, and the interaction Hamiltonian. At this time, the coupling between the transmission line mode and the artificial atom is mediated by the atom charge operator. That's why it is called the charge gauge. Okay, and nicely enough, this charge gauge has the opposite behavior as the flux gauge, because if you go to high frequency, the coupling to the transmission line goes to zero. So there's an asymptotic freedom which emerges at high frequency. So it is possible to truncate the theory at high frequency without any problem. And the other nice property is that the atom Hamiltonian has fixed parameters. So there is a zero renormalization by the transmission line. So you have this kind of quantum Hamiltonian for the charge and flux operators with parameters which are fixed. It would depend only on the fluxonic parameter. The only price to pay in this gauge is that if you look at the coupling to the low frequency mode, this can be ultra strong. In particular, if you look at the first mode, the vacuum Rabi frequency, which quantifies the coupling to this mode, can be much larger than the frequency of the first mode. So you have in the ultra strong coupling regime. But the ultra strong coupling to the low frequency mode can be conveniently treated through the so-called polar transformation, which I will describe here. So basically, we will perform a two-level approximation for the artificial atom, which is well justified due to the strong anharmonicity of the fluxonium atom. And so basically, we can describe the atom Hamiltonian in terms of Pauli matrices. And then if you look at the transition associated to the level system, this transition energy depends on the external flux, which is the magnetic bias, which can be applied to the system. It has this typical dispersion. So the energy of the atom can be tuned via the external flux bias. And then basically, once we do the two-level transformation, the polar transformation is a unitary transformation that depends on this on the Pauli matrix sigma y, if you use this convention, and this operator B, which is the sum of bosonic operators for the different low frequency modes. And the coefficient alpha I is the dimensional quality, which is actually proportional to the ratio between the mode coupling and the mode frequency. So when the mode coupling is very large compared to the frequency, this alpha I is large. And if you perform this polar transformation, what happens is that we get this final Hamiltonian, which is quite compact. So basically, the coupling to the low frequency photonic modes is responsible for this dispersive Hamiltonian. So basically, the qubit, the Fluxonian Hamiltonian, is modulated by this cosinus and sinus operator, which are a function of the operator B. I just remind you this, the operator B is the sum of the operator BI, which are associated to the low frequency mode. So B is linear in the bosonic operators for the low frequency mode. Now, since the cosinus and sinus can be expanded in a Taylor series, we understand from this simple fact that actually cosinus B, sinus B, describes multi-photon processes involving the low frequency photon. And the cosinus involves only processes involving an even number of photons, and the sinus an odd number of photons. So basically, we see that the coupling to the low frequency photons is responsible to a modulation of the qubit Hamiltonian via these multi-photon processes involving low frequency modes. Then there is the energy of the modes, and then the standard direct coupling between the qubit and the high frequency transmission line modes. Okay, now let's start by first completely neglecting the low frequency mode. So which are the eigenstates of the system? The single excitation eigenstates are polariton-like states, which are described here. So basically, one polariton is basically the linear superposition of a state which consists of the atom in the excited state at 0 photons and single photon states on the different modes. And the W are actually the polaritonic weights, respectively, for the atom and for the single photon state. The larger the coupling, the more the polaritonic modes spreads over the original bare transmission line modes. Now, if you switch on the interaction with the low frequency modes, you have these multi-photon processes which I've described before. So here you can see the simplest process, which basically you start from a single polariton in mode K, which is coupled by the sinus B operator into a state with a single polariton in another mode K prime, and the low frequency photon in mode I. And so this cartoon just describes this kind of coupling. And this kind of coherent Hamiltonian coupling matters when the energy of the left state is close to the energy of the right state, which gives to this resonant coupling condition. So the energy of the K polariton is equal to the energy of the K prime polariton plus the energy of one frequency photon. And if you have this kind of coherent coupling, basically, when you are at the resonant condition, we can anticipate that there will be some kind of multi-photon anti-crossing due to this coherent coupling. But this is the simplest process because you can have multi-photon processes, which are described here. And the matrix elements for this generic multi-photon process, where you have one polariton state on the left with some numbers of photons in the low frequency mode, and another state of the same time, but with another mode K prime and another number of photons on the right side. Actually, this is a generic multi-photon process we can calculate the matrix elements associated to this process. The result is cumbersome, but it can be calculated analytically. For this simple process, the matrix element are significantly simplified. And you can see, basically, you have the matrix element associated to this process depends on a prefactor, lambda, which depends on the dimensional coupling alpha I described before. And it's a linear for this process in alpha I. So for small couplings, lambda increases with the dimensional less coupling alpha I. But when the coupling becomes very large and alpha I becomes comparable to 1, there is an exponential suppression. So basically, the effective coupling is the compromise between these two terms. And then the other relevant terms are the polaritonic weight, in particular the atomic weight in polariton mode, K, K prime, which are involved in the multiphoton process. Okay, so let's look at experiments now. So these are linear reflection spectra achieved by the experimental groups led by Vladimir Manasharin at the University of Maryland, Joint Quantum Institute. So basically, here you see the linear reflection, so low intensity spectroscopy. You see linear reflection spectra is a function of the frequency and of the flux bias. So the flux bias is an applied magnetic field which is able to shift the frequency of the Fluxonion transition. And on the left, you can see a panoramic view on a wide range of frequency. For example, here it's more than alpha gigahertz. And you can see the flat part of the dispersion is the dispersion of the transmission line nodes. And you can see there are nice anti-crossings, which are due to the hybridization between the transmission line nodes and the Fluxonion transition. So these are the polaritonic anti-crossings described before. Okay, this is quite a standard physics all in polarity. But then these are results for a sample with x equals 7%. So the coupling between two-level system and the transmission line nodes is rather small. But then if you zoom this region, you can see there is a fine structure with many smaller anti-crosses. And you can understand that the origin of this anti-cross, if you take, for example, one polarity dispersion and you shift by one low frequency photon, and at the crossing points, you can describe the first crossing point. So the fact that this anti-crossing appears where there is the crossing between the shifted polarity branch and this branch, it's really a demonstration of the fact that this anti-crossing is due to the multiphoton process. And then it can generalize this to two-photon process. You have another anti-crossing. Then you have different photon frequency. You have different anti-crossing. And if you calculate the linear reflection spectra by using the theory which I've described just earlier, you can find a quite spectacular agreement. And the only adjustable parameters are the parameters of the Fluxonion atom, which I actually are very close to the nominal one. Okay, but this is for 7%. If you increase the coupling, what happens is that if you have a 50% coupling, you can see that now you don't need to zoom to see the splitting. You have a jungle of multiphoton anti-crossing, which match very well with our theory. And so you have many more anti-crossing and larger split. But now, if you increase further the coupling, this is something which we are still now studying theoretically. This will go into a much challenging domain. Well, you see that when you increase further the coupling, basically there are many channels that are open. So when you increase the coupling, there are many channels which are open. And also in this system, you have to, I remind you that the Josephson junction in the transmission line resonator are in the number of 20,000. So there is some small disorder in the system, even it's quite moderate. So there is basically, if you increase the coupling, you have many channels which are open, a lot of many body processes, which these many body processes emerge in the presence of a small residual disorder. And so what happened? is that basically the splittings disappear and there's a spectral collapse. So basically, there is a transition between a many-body anti-crossing with discrete splittings to a spectral collapse. And this is an exciting field which is still understudied, but these results strongly suggest that due to the many photon interaction mediated by the single two-level system acting as a quantum purity, basically there is a transition towards basically the transmission line, thanks to the mediation of the two-level system, become its own bus. This is suggestive of a quantum thermalization of this quantum system. Okay, and just to finish, I will, in the next 5–10 minutes, I will talk about third topic, which is basically the application of open quantum many-body system to understand ion entangling quantum information in the context of quantum information. In particular, we will describe the quantum Fourier transform. Okay, so here you can see the quantum Fourier algorithm. So basically on the left, you can see the register of L quantum bits. And so basically the quantum Fourier transform is achieved by a sequence of a single gate and two gate operations, in particular Hadamard gate and the control phase gate. And by a judicious sequence of these single and two qubit gates, at the end, the system evolves in a unitary way towards a final state, which is used to calculate the quantum Fourier transform. But in real systems, this kind of unitary evolution can be actually coexist with dissipation processes, which are schematically represented by these wavy lines and the dissipation rate count. So basically, our goal is to use the techniques of open quantum many-body system to expand the number of qubits that can be simulated classically in order to help the development of quantum hardware architectures. And in particular, we wish to optimize techniques which are mostly suited for high entanglement and low entropy quantum circuits. In fact, the quantum Fourier transform is high entangling quantum circuit. And if you consider the state of the art quantum systems, the goal is to have a pure state dynamics. So you want to have a system with a low entropy quantum, low entropy value. And then we want also to model the continuous time dynamics of these quantum errors without approximating the errors with digitized and local error. In other way, we want to solve the master equation for this kind of quantum circuit in presence of dissipation. And that's what we have done. But to do that, we have developed a technique which is, allows us to optimize the dynamics of an open quantum many-body system in the low entropy regime. So in the following, n will be the Hilbert space dimension, which is very large, okay? For 21 qubits is extremely large, for example. And then m is the corner space dimension. So basically the idea is to represent, the density matrix can be always expanded in terms of its eigenstates and of the probability values. Now, if you truncate and you take the m most probable eigenvalues, you do an approximation, and the error associated to this approximation is basically 1 minus the sum of the probabilities for the k between 1 and m. And so what we want to do is we want to represent the density matrix in such corner space by truncating the density matrix by keeping the error always smaller than a fixed value epsilon. And we are interested in the low entropy regime when the dimension of this corner space is much smaller than n. And just as a reminder, when you have a pure state, the entropy is equal to 0, and you can exactly represent the density matrix with just one state, which is the pure state. Okay. Now, I will show the algorithm which we have developed to optimize the time-dependent dynamics in this low entropy regime. So first of all, we don't want to keep in memory the large density matrix, which is a very large n by n density matrix. So what we do, we encode the density matrix, this smaller matrix C, which is a rectangular matrix. So rho is C times C dagger. And if you, n is the basis of the full Hilbert space, C is actually a matrix whose columns are the eigenstates of the density matrix in the corner space, weighted by the square root of the corresponding probability. So the density matrix can be encoded into a smaller density matrix like that. Then we consider the dynamics for an infinitesimal time delta t. And the density matrix dynamics for a small delta t can be expressed in terms of so-called Krauss operators, okay? So, which I will describe in the next slide. So the evolution of the density matrix is linked to the density matrix at the previous time, transformed via these Krauss operators. And once we get the density matrix at this later time, t plus dt, we can encode the density matrix via this T matrix, which basically contains this new transition basis. And so basically this transition basis encoded in T is obtained by applying the Krauss operator into the initial basis file. And okay, so which are these Krauss operators? So if we have D dissipation channel, there are D plus 1 Krauss operators. The K0 operator is just the evolution operator, the non-unitary evolution operator associated to the non-Hermitian matrix, Hamiltonian matrix, which is the Hamiltonian of the system, minus I times this operator, which is given by the jump operators. And the Krauss operators, I from 1 to D, are proportional to the jump operator. So basically, if you consider you have the corner space at the time t, you have the basis of the corner, the orthonormal basis of the corner space, you apply all the possible Krauss operators, and that's how you get this transition basis, which is encoded in this rectangular matrix T. And now what you do, you select, you use this matrix T to calculate the eigenvalues of the density matrix at time t plus the delta t. In fact, if you calculate the matrix T dagger T, this is a small matrix compared to the density matrix, which can be diagonalized. The nice property of this matrix sigma is that it has the same eigenvalues as the density matrix with this eigenvector. So basically, we can find the eigenvalues, the eigenvector of the density matrix without putting into memory the large density matrix. And once we have these eigenvalues, we chose the largest eigenvalues, that means the most probable, and so we can update the corner space basis at the time t plus dt. And this procedure can be iterated at each time step. And the important thing and to keep in mind is that the density matrix is never stored in memory. We store in memory just the smaller matrix C, which is the dimensions of the Hilbert space times the dimension of the corner space. And this, if the system has a moderate entropy, is much smaller than m squared. That's the advantage that we get. And there is a clear connection between the present method and the Monte Carlo wave function method, which was pioneered by Jean Dalibard, Yves Castin, and Klaus Mommern. So the idea of the Monte Carlo wave function is to consider individual wave function trajectory. And each wave function trajectory is given by the deterministic evolution via the very same non-Hermitian Hamiltonian, which was introduced early in the context of Krauss operators. But then on top of the deterministic evolution, there are random quantum jumps which are applied to each individual trajectory, and they're obtained via the jump operators. And then once each individual trajectory is obtained, the dynamics is repeated, each trajectory is different. And the observables are obtained by averaging over different quantum trajectories. The nice thing of the Monte Carlo wave function method is that only the wave function is stored in memory, not the density method. It can be parallelized. This is a stochastic method, and in general, the trajectories are non-orthogonal, so there is some redundancy. But when the system has a low entropy, the wave function Monte Carlo can be generalized in a deterministic way as we did, because basically what we are doing is just to generate in a systematic way all the possible wave function trajectories via the Krauss operator, and we are selecting the n most probable one. And in other words, this works only if the system has a low entropy, because the method is analogous to solve n-closed systems, which is much simpler than consider the density matrix in all the Hilbert space. And so we apply that with success to the quantum Fourier transform. And so basically, we consider the master equation for this quantum circle with dissipation. This quantum Fourier transform can be implemented in this way. So if you associate to each qubit a spin, the single qubit gate is the Hadamard gate. Okay, it can be obtained by applying the Hamiltonian H1, the spin Hamiltonian H1 for this time T1. Followed by Hamiltonian 2 applied for the time T2. With this kind of dynamics, we get an Hadamard gate. The control phase gate can be obtained by applying these two spin-spin Hamiltonian for this time Tc. And this realizes these two qubit gates. And then the dissipation is obtained by jump operators. In the case of dissipation, the jump operator is the sigma minus operator on the qubit I. In the case of pure dephasing, the jump operator is the sigma z operator. Okay, these are the results which are obtained with the time-dependent corner dimension. So here we are plotting the corner space dimension as a function of time at the entropy. Actually, it's the exponential of the fundamental. You can see when the time goes on, the entropy increases. That's the source of error because the system becomes mixed. Density matrix has a finite entropy. And you can see that the dimension of the corner space is dynamically adjusted. And when the entropy increases, gradually the dimension of the Hilbert space is increased. So notice that not only the dimension of the Hilbert space of the corner space is increased, but also the corner space basis is rotating. So basically, our algorithm is adjust the dimension of the corner space to take into account for the entropy, and also optimally adjust the basis to find the optimal trajectory. And on the top of the bottom panel, you can see the entanglement entropy, which quantifies the entanglement for pure system. You can see that this plot, just to make it simple, you can see that when the time advances, the entanglement spreads over all the qubits. Indeed, the quantum Fourier transform is highly entangling quantum circuit. It is used, for example, for the Shor algorithm for the factorization of prime numbers. Okay, just to show you that the method has been successfully benchmarked. So here you can see rho C gamma is the density matrix obtained with the time-dependent corner method, and the rho gamma is the exact density matrix obtained by brute force integration of the master equation. So the benchmarking has been done for a small number of qubits, and you can see that you can have very small infidelities, and when the dissipation decreases for a given corner space dimension, the infidelity drops dramatically. And you can see also how this scales with a number of qubits. Okay, so far so good. Just it's quite interesting to look at the simulation time. So if you show the simulation time of the brute force numerical integration as a function of the number of qubits, you can see it's exponential. With our method, it's already exponential, but with a smaller slopes. Okay, the method the dependence of the simulation time on the number of qubits must stay exponential, because if this was not the case, there would be no quantum advantage with the quantum Fourier transform. So what our method does is to flatten the curve and to diminish the slopes, and this allows us to simulate a larger number of qubits that can be done. And for example, for 21 qubits, the Hilbert space is larger than 2 million, but we could converge with this kind of dissipation with just 50 states. So this is an incredible simplification. And what we have found is that, for example, if you look at the pure result of the quantum Fourier transform, this is a pure density matrix in the case of no dissipation. So rho zero is the output of the quantum Fourier transform algorithm without dissipation. Now, if you calculate the infidelity between such pure result and the result with dissipation, we have been able to study how this infidelity scales with the number of qubits. And quite remarkably, we have found that such infidelity scales quadratically with the number of qubits, something which was not known in the literature, at least to the best of our knowledge. Just to give you an example that we can understand how error propagates using continuous time dynamics without any approximation for the error. And it's quite interesting also to look at the dependence of the initial state. In fact, here you can see the infidelity plotted as a function of two parameters which characterize the initial state. And in the case of the dissipation, you can see there is a dramatic dependence of the initial state. In particular, if you do the spin analogy for the qubit, the infidelity is very sensitive to the number of spins up, and there is an asymmetry between spin up and spin down due to the dissipative channel. And also there is a dependence on the spin barycenter. In fact, if you look at the quantum Fourier algorithm, you can see that the operation starts from the top qubit and finishes to the bottom qubit. So there is an asymmetry between high-level qubits and low-level qubits. And in the presence of dissipation, this translates into a dependence on the so-called spin-up barycenter. But if you do the same calculation with the pure dephasing channel, you can see that there is no dependence on insertion. Just to give you an example. And the bottom line is that this is quite exciting. As a perspective, it would be very interesting to integrate this time-dependent corner space method with other methods that can efficiently represent the corner space, for example, neural network wave function, with the same goal to extend the number of qubits that can be simulated classically to help the development of quantum hardware architectures. And there are many applications to several physical magic quantum platforms, for example, rayonnement atoms, ion traps, superconducting qubits, photonic systems. And so that was the end of the talk. And I'm now very pleased to collaborate all the theoretical team at the Laboratoire Matériaux, phénomènes, quantique. And I'm very happy of the exciting collaboration which we had during the years. And I thank you very much for your attention. Thank you very much.